Tonight, we are going to talk about one of the most important events that ever happens in the universe. It is not a planet forming. It is not a galaxy colliding. It is not even a black hole feeding. It is the moment a star loses control of itself and releases more energy in a few seconds than our sun will produce in its entire lifetime. This moment is called a supernova. Supernovae are not just explosions in space. They are turning points. They decide what the universe becomes next. Every atom in your body, every planet, every complex structure owes its existence to these violent stellar deaths. To understand supernovae is to understand how the universe builds itself through destruction. A star spends almost its entire life fighting gravity. From the moment it forms, gravity tries to pull all of its mass inward, crushing it toward collapse. The only thing that stops this from happening is energy. Deep inside a star's core, nuclear fusion releases energy that pushes outward. This outward pressure balances gravity perfectly. As long as that balance holds, the star remains stable. It shines. It lives. But this balance is fragile. It depends entirely on the star's ability to produce energy. And eventually, every star reaches a point where it can no longer do that. For small stars like the Sun, this ending is relatively gentle. But for massive stars, the ending is catastrophic. A massive star burns through its fuel much faster than a smaller one. It lives fast and dies young. As fusion continues, the star builds heavier and heavier elements in its core. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen. The process continues, building layers like an onion, each one fusing a heavier element than the last. But there is a limit. Fusion can only produce energy up to a certain point. When iron forms in the core, the process stops. Iron is the end of the line. Fusing iron does not release energy, it consumes it. The moment a massive star begins forming iron in its core, the star is already doomed. Energy production collapses. The outward pressure that once held gravity back disappears. Gravity immediately takes over. The core collapses inward at an unimaginable speed. In less than a second, the core of the star implodes, crushing protons and electrons together to form neutrons. The core shrinks from something larger than Earth to something only a few kilometers wide. This collapse is so violent that it creates a shock wave. Matter falls inward, slams into the newly formed core, and rebounds outward with enormous force. Neutrinos flood out. Energy is released in staggering amounts, and in a fraction of a second, the outer layers of the star are blown apart. The star does not simply explode, it tears itself open from the inside. This is a supernova. For a brief moment, the dying star outshines entire galaxies. Its light can be seen across billions of light years. It releases more energy than the sun will produce over billions of years. But the explosion itself is only part of the story. The real importance of a supernova lies in what it creates and what it leaves behind. Inside that explosion, conditions become extreme beyond anything else in the universe except black holes. Temperatures reach billions of degrees. Pressures become so intense that atomic nuclei collide and merge. Elements heavier than iron are forged in these moments. Gold, silver, uranium, iodine, and countless other elements are created not in stars, but in supernovae. These elements are then scattered across space, mixed into gas clouds that will one day form new stars, new planets, and eventually life. A supernova is not the end of creation. It is the engine of creation. Without supernovae, the universe would contain almost nothing but hydrogen and helium. There would be no rocky planets, no complex chemistry, no life. Every time a supernova explodes, it enriches the universe, seeding it with the materials needed for complexity. What remains at the center of a supernova depends on the mass of the original star. In some cases, the collapsed core becomes a neutron star, an object so dense that a single teaspoon would weigh billions of tons. In other cases, gravity wins completely, and the core collapses into a black hole. Either way, the supernova marks the birth of some of the most extreme objects in existence. Neutron stars and black holes are not separate phenomena. They are the aftermath of supernovae. Supernovae also shape galaxies. The energy they release heats surrounding gas, triggers new waves of star formation, and prevents galaxies from collapsing too quickly. They act as regulators, controlling how matter moves and settles. Entire regions of galaxies owe their structure to ancient supernova explosions. The Milky Way itself is filled with the remnants of stars that died long before the sun was born. When we look at a supernova in the sky, we are not just witnessing an explosion. We are watching a fundamental process that keeps the universe evolving. It is gravity pushing too far, energy failing to keep up, and nature responding with one of the most dramatic events it allows. A supernova is what happens when balance breaks. And once it breaks, the universe is never the same again. Some supernovae begin with a single massive star reaching the end of its life. These stars are born large, burn their fuel quickly, and die violently. From the moment they form, gravity and fusion are locked in a race. The star shines brightly, consuming hydrogen at a furious rate. As millions of years pass, the core grows heavier, fusion builds new elements, and gravity tightens its grip. Eventually, the star reaches the iron limit, energy production collapses, and gravity wins in an instant. The core implodes, rebounds, and the outer layers are torn away. This type of supernova is driven by core collapse. It is the natural death of a massive star. Other supernovae begin far more quietly. They start not with a giant star, alone, but with a star in a close partnership. In these systems, a dense stellar corpse called a white dwarf orbits another star. A white dwarf is what remains when a sun-like star finishes its life. It is compact, dense, and stable, held up by quantum pressure rather than fusion. On its own, a white dwarf can exist for trillions of years without change. But when it has a nearby companion, everything changes. Over time, the white dwarf pulls matter from its partner star. Gas spirals inward, settling onto the white dwarf's surface. As mass accumulates, pressure and temperature rise. The white dwarf grows heavier, approaching a critical limit. There is a precise threshold beyond which the white dwarf can no longer support itself. When that limit is crossed, fusion ignites throughout the star almost simultaneously. There is no slow burn. There is no balance. The white dwarf detonates completely. Nothing is left behind. The star is destroyed in a thermonuclear explosion that releases a predictable amount of energy. This is another kind of supernova, one that does not create a neutron star or black hole, but instead erases the star entirely. These two paths to destruction produce explosions that may look similar from a distance, but they come from very different origins. One is driven by gravity overwhelming fusion. The other is driven by fusion overwhelming stability. One leaves behind a compact remnant. The other leaves nothing at all. Together, they show that supernovae are not just about size or age. They are about balance, mass, and environment. The differences between these supernovae matter because they shape the universe in different ways. Core collapse supernovae scatter heavy elements forged during the star's life and during the explosion itself. They create neutron stars and black holes, objects that will continue influencing their surroundings for billions of years. Thermonuclear supernovae scatter large amounts of iron and other elements that play a key role in planetary formation and chemistry. Because these explosions are so consistent in brightness, they also serve as cosmic distance markers, allowing astronomers to measure the expansion of the universe. Supernovae also differ in how they interact with their surroundings. A massive star often lives in a region rich with gas and other young stars. When it explodes, its shockwave slams into nearby material, compressing it and triggering new rounds of star formation. In this way, death leads directly to birth. A thermonuclear supernova, on the other hand, may occur in older regions of a galaxy, where star formation has largely ended. Its explosion enriches space chemically, but may not trigger many new stars. These differences help explain why galaxies evolve the way they do. What unites all supernovae is scale. No matter the cause, the energy released is immense. The explosion expands outward at thousands of kilometers per second. Shockwaves travel through space for tens of thousands of years. The glowing remnants remain visible long after the initial flash fades. These remnants are not debris fields. They are active regions where matter mixes, magnetic fields twist, and particles are accelerated to extreme energies. Some of the highest energy particles detected on Earth likely originated in supernova remnants scattered across the Milky Way. Supernovae also reveal something important about predictability in the universe. Some explosions follow consistent patterns. Others vary wildly. Small differences in mass, rotation, or environment can change how a star dies. This sensitivity shows that the universe operates near critical thresholds. Push a system slightly past balance, and the outcome can change dramatically. Supernovae are the clearest examples of this principle on a cosmic scale. By studying different supernovae, astronomers can reconstruct the lives of stars long after they are gone. The light from an explosion carries information about the star's composition, its mass, and its environment. The shape of the remnant reveals how the explosion unfolded. Even centuries later, scientists can piece together the final moments of a star that died before modern science existed. Supernovae turn stellar death into readable history. Despite their violence, supernovae are not rare in the universe as a whole. Somewhere in the observable universe, a supernova explodes every second. Most occur too far away to see with the naked eye, but their cumulative effect shapes everything. They regulate star formation, distribute elements, and energize galaxies. Without them, the universe would stagnate. With them, it evolves. Supernovae also remind us that the universe does not waste energy. Nothing about these explosions is random or meaningless. Every burst of light, every shockwave, every newly formed atom becomes part of the cosmic cycle. Matter is destroyed, but structure increases. Energy is released, but order emerges. This is one of the deepest patterns in nature. Destruction is not the opposite of creation. It is often the path to it. When we look at the remains of a supernova, we are looking at a transition. A star has ended, but something new has begun. New elements exist. New objects form. New stars may be triggered. The universe moves forward, reshaped by a single moment of imbalance. A supernova is not just a death. It is a transformation written in light. A supernova may take millions of years to prepare, but the event itself unfolds in an instant. In just a few seconds, the internal structure of a star collapses, rebounds, and reshapes its surroundings forever. These seconds matter more than the entire lifetime of the star that came before them. They are the moment when the universe concentrates unimaginable energy into a brief, violent release, and in doing so, unlocks processes that cannot occur anywhere else. As the core of a massive star collapses, gravity accelerates matter inward faster and faster. The collapse is so extreme that electrons are forced into protons, forming neutrons and releasing a flood of neutrinos. These neutrinos escape almost instantly, carrying away vast amounts of energy. For a brief moment, the collapsing core becomes one of the densest places in the universe. Space itself responds to the sudden concentration of mass. Time slows. Light struggles to escape. Physics enters a regime where familiar rules no longer apply cleanly. When the inward collapse halts, the core stiffens abruptly. Neutron pressure pushes back against gravity, and the imploding matter slams into this newly formed core. The result is a shockwave that races outward. At first, this shockwave struggles. It loses energy as it moves through the star's dense interior. For years, scientists debated whether the shockwave alone could power a supernova. The answer appears to be no. Something else helps drive the explosion. That something is the flood of neutrinos released during the collapse. Neutrinos are nearly massless particles that interact weakly with matter. But in a supernova, their sheer numbers change everything. Trillions upon trillions of neutrinos pass through the surrounding material, transferring energy just enough to revive the stalled shockwave. This revived shockwave tears through the star, ripping it apart from the inside. In a matter of seconds, layers that took millions of years to form are destroyed. The star does not explode outward like a bomb. It is pushed apart by an internal catastrophe that gravity itself initiated. During these moments, conditions become extreme beyond description. Temperatures soar into the billions of degrees. Atomic nuclei collide violently. New particles appear. Forces that normally act gently become dominant. This is when the universe performs one of its most important acts of creation. Heavy elements begin to form. Gold, platinum, uranium, and many other elements are forged as neutrons are rapidly captured by atomic nuclei. These elements cannot form inside normal stars. They require the chaos and intensity of a supernova. The explosion does not occur evenly in all directions. Modern observations show that supernovae are often asymmetric. Jets, clumps, and uneven shock fronts appear. The star tears apart in a complex, turbulent process. This asymmetry affects what remains behind. It influences whether a neutron star forms cleanly or whether the core collapses further into a black hole. It also shapes the distribution of material ejected into space, determining where new stars may eventually form. For a brief time, the supernova becomes the brightest object in its galaxy. The light travels outward, crossing interstellar and intergalactic space. By the time it reaches Earth, it may have traveled for millions or billions of years. Yet it still carries the signature of those few seconds at the star's core. The spectrum of the light reveals which elements were formed. The timing reveals how the explosion unfolded. Even centuries later, astronomers can reconstruct those moments from the fading glow of the remnant. After the initial flash, the expanding debris continues to evolve. Shockwaves race outward, colliding with surrounding gas. Magnetic fields twist and strengthen. Particles are accelerated to nearly the speed of light. These particles become cosmic rays, some of which eventually reach Earth. In this way, supernovae connect the most distant events in the universe to our own planet. Atoms forged in ancient explosions and particles accelerated in distant remnants are part of our everyday environment. What remains at the center of the explosion depends on how massive the original star was and how the collapse unfolded. In some cases, the core stabilizes as a neutron star, spinning rapidly and emitting intense radiation. In others, gravity overwhelms all resistance, and a black hole forms. These remnants are not passive leftovers. They continue interacting with their surroundings, shaping space through gravity and radiation long after the explosion has faded. The few seconds of a supernova are a transition point. They mark the moment when a star stops being a star and becomes something else entirely. The energy released in that moment determines the future of the surrounding region for millions of years. New stars may form from the compressed gas. New planets may one day assemble from the enriched debris. Entire star systems may owe their existence to a single ancient explosion. Supernovae also reveal how tightly connected different scales of the universe are. Processes happening deep inside a collapsing core influence galaxies, clusters, and even intergalactic space. What begins as a failure of balance inside one star becomes a source of structure across vast distances. This connection between the smallest and largest scales is one of the defining features of cosmic evolution. The universe does not create complexity gently. It creates it through moments like these. Through collapse, through shock, through release. A supernova is the universe concentrating millions of years of energy into a few seconds and using that energy to build something new. Those seconds are brief, but their consequences last forever. When the light of a supernova fades, the story is far from over. In many ways, the explosion is only the beginning of a much longer transformation. What remains after a supernova is not silence or emptiness, but a vast, expanding structure known as a supernova remnant. These remnants are among the most important and dynamic regions in the universe. They are places where energy continues to flow, matter continues to mix, and the future of entire star systems is quietly decided. A supernova remnant begins as a rapidly expanding shell of debris. The outer layers of the star, once held together by gravity, race outward at thousands of kilometers per second. This expanding material slams into the surrounding interstellar gas, creating powerful shock waves. These shocks heat the gas to millions of degrees, causing it to glow in X-rays, radio waves, and visible light. What we see in telescopes is not a static cloud, but a living structure, constantly changing as it expands and cools. Inside these remnants, matter behaves in extraordinary ways. The explosion has scattered heavy elements forged in the star and during the supernova itself. Oxygen, silicon, iron, and many other elements are now mixed into the surrounding space. These elements do not spread evenly. They form knots, filaments, and bubbles shaped by turbulence and magnetic fields. Over tens of thousands of years, this material slowly disperses, becoming part of the interstellar medium. Long after the explosion, the remnant continues to enrich space with the raw ingredients needed for new stars and planets. Supernova remnants are also some of the most efficient particle accelerators in the universe. As shockwaves move through space, they trap charged particles and accelerate them to nearly the speed of light. These particles become cosmic rays, high-energy messengers that travel across the galaxy. Some of them eventually strike Earth, carrying information about violent events that occurred long before the Sun formed. In this way, supernova remnants connect distant stellar deaths to our own environment in a direct and physical way. At the center of many remnants lies the core that survived the explosion. In some cases, it is a neutron star, spinning rapidly and emitting intense beams of radiation. These neutron stars can be detected as pulsars, objects that flash with clock-like precision as they rotate. Each pulse is a reminder of the moment the star collapsed. The neutron star is incredibly dense, incredibly stable, and incredibly long-lived. It may continue emitting radiation for millions or even billions of years, long after the surrounding remnant has faded into invisibility. In other cases, the core collapses further and becomes a black hole. Unlike neutron stars, black holes do not announce themselves with beams of light. They reveal their presence only through their gravitational influence. In some remnants, the absence of a visible core is itself evidence of a black hole's birth. These black holes may remain isolated, or they may later interact with surrounding material, forming new sources of radiation. Either way, the supernova marks their creation. Supernova remnants are not just leftovers, they are engines of change. As the expanding shell sweeps through space, it compresses nearby gas clouds. This compression can trigger new waves of star formation. In this way, the death of one star directly contributes to the birth of many others. Entire star-forming regions may trace their origins back to a single ancient explosion. The universe recycles itself through supernovae, turning endings into beginnings. Over time, the remnant slows. The shock waves weaken. The glowing gas cools. Eventually, after tens or hundreds of thousands of years, the remnant fades into the background of the galaxy. At this point, it becomes indistinguishable from the interstellar medium, but its influence remains. The chemical makeup of the galaxy has changed. The distribution of gas has shifted. New stars may already be forming from the enriched material. The supernova's legacy is complete, woven into the structure of the galaxy itself. Supernova remnants also serve as cosmic records. By studying their shape, composition, and motion, astronomers can reconstruct the details of the explosion. They can determine how massive the original star was, how fast the debris expanded, and how the explosion interacted with its surroundings. Even for supernovae that occurred thousands of years ago, the remnants preserve enough information to tell their story. In this way, remnants act like fossils, preserving moments of cosmic history long after the initial flash has faded. Some of the most famous objects in astronomy are supernova remnants. They appear as delicate filaments, glowing arcs, and expanding shells that fill entire regions of space. These structures are not only beautiful, but deeply informative. They reveal the interplay between energy, matter, and magnetic fields on scales far beyond anything humans can create. They show us that the universe does not simply move forward in time. It remembers its past in structure and form. Supernova remnants also help explain why galaxies do not collapse under their own weight. The energy injected by countless explosions over billions of years heats galactic gas and keeps it from falling inward too quickly. This ongoing energy input helps maintain the balance between gravity and motion on galactic scales. Without supernova remnants constantly stirring and heating the interstellar medium, galaxies would evolve very differently. They would form stars too rapidly and exhaust their fuel too soon. In this sense, remnants are part of a larger system of regulation. Stars form, stars die, energy is released, matter is recycled, and the process begins again. Supernova remnants are the visible expression of this cycle. They show us that the universe is not a place of simple, linear progress, but one of continuous transformation. What is most striking about supernova remnants is how long their influence lasts compared to the explosion itself. The supernova may last days or weeks as a visible event, but the remnant shapes space for tens of thousands of years. The briefest moments can produce the longest consequences. This pattern appears again and again in the universe. Short bursts of intensity create structures that endure. When we look at a supernova remnant, we are looking at time made visible. We see the past expanding into the present. We see energy turning into structure. We see the universe processing change. The remnant is the universe settling into a new configuration after a moment of extreme imbalance. A supernova does not end when the star explodes. It continues in motion, in chemistry, and in structure. The explosion fades, but its influence spreads outward, shaping everything that comes after. A supernova does not simply destroy a star. It transforms it. At the heart of every supernova lies a choice made by gravity, a decision shaped by mass, pressure, and the limits of physical law. When the explosion tears the outer layers of a star apart, the core is left exposed to its own weight. What happens next determines whether the star's story truly ends or continues in a new, far more extreme form. If the core is not too massive, gravity compresses it until neutrons press tightly together, forming a neutron star. This object is one of the most extreme forms of matter that can exist without collapsing completely. A neutron star packs more mass than the Sun into a sphere only a few kilometers wide. The density is so high that atoms cannot exist. Matter becomes a sea of neutrons, held together by forces that operate only under unimaginable pressure. In this state, gravity is balanced not by fusion, but by the resistance of matter itself at the quantum level. A newborn neutron star is not quiet. It spins rapidly, often hundreds of times per second, conserving the angular momentum of the collapsing core. Its magnetic field intensifies dramatically, becoming trillions of times stronger than Earth's. As it rotates, beams of radiation sweep through space like cosmic lighthouses. When one of these beams crosses Earth, we observe a pulse of light. These objects are known as pulsars, and they are some of the most precise clocks in the universe. Each pulse marks the continued survival of a star that refused to collapse completely. In some cases, the neutron star is even more extreme. Its magnetic field becomes so strong that it begins to affect space around it directly. These objects, called magnetars, can crack their own crusts and release bursts of energy that briefly outshine entire galaxies in gamma rays. Even long after the supernova has faded, the remnant core remains a source of intense activity. The explosion is over, but the consequences continue. If the core is more massive, even neutron pressure cannot stop gravity. The collapse continues. Matter is compressed beyond the limits of known physics. Space-time curves inward without restraint. An event horizon forms. A black hole is born. In this case, the supernova marks the creation of an object from which nothing can escape, not even light. The star does not leave behind a visible remnant. It leaves behind an absence defined only by gravity. These black holes are not necessarily inactive. If material remains nearby, it may fall inward, releasing energy as it does so. Over time, black holes formed in supernovae can grow, merge, and become the massive objects that power quasars and shape galaxies. In this way, supernovae are not only endings, they are beginnings for some of the most influential objects in the universe. The difference between forming a neutron star and a black hole can depend on subtle factors. A small change in mass, rotation, or composition can tip the balance. This sensitivity shows how close stars operate to the edge of stability. The universe often builds its most extreme objects by pushing systems just slightly beyond equilibrium. Supernovae are the moments when that balance finally breaks. The remnants left behind by supernovae also act as laboratories for physics. Neutron stars allow scientists to study matter at densities far beyond anything achievable on Earth. Their behavior reveals clues about the fundamental forces that hold atomic nuclei together. Black holes test our understanding of gravity itself, especially under extreme curvature of space-time. Every supernova remnant is a gateway to deeper knowledge about how reality behaves under conditions that cannot be replicated in any experiment. These remnants also influence their surroundings long after their birth. Neutron stars emit winds of particles that energize nearby space. Black holes warp the motion of stars and gas around them. Over millions of years, these influences shape local regions of galaxies. The death of one star can determine the fate of many others nearby. There is something profound in this transformation. A star that once shone steadily for millions of years ends its life in chaos, only to leave behind an object that may persist for billions of years more. The universe trades one form of stability for another. Light becomes gravity, fusion becomes density, motion becomes curvature. Nothing is wasted. Everything is transformed. Supernovae show us that the universe does not erase information easily. The history of a star is encoded in its remnant. The mass of a neutron star, the spin of a black hole, the composition of surrounding debris all carry traces of what came before. By studying these remnants, astronomers can reconstruct the life and death of stars long gone. Supernovae turn endings into records. The creation of neutron stars and black holes also connects supernovae to the most extreme phenomena we observe today. Pulsars, magnetars, gravitational waves from merging compact objects, and even the growth of supermassive black holes all trace their origins back to stellar explosions. The universe's most violent and mysterious events often begin with a supernova. In this way, supernovae act as gateways. They are the points where ordinary stars give way to extraordinary objects. They link the familiar physics of fusion and light to the exotic realms of extreme gravity and dense matter. They show us that the universe builds its most powerful structures through collapse, not through expansion. A supernova is not just a moment of destruction. It is the moment a star becomes something entirely different. And what it becomes can shape the universe for billions of years. A galaxy is not shaped only by gravity pulling matter inward. It is shaped just as much by energy pushing outward. Supernovae are one of the most important sources of that outward push. They act as regulators, preventing galaxies from collapsing too quickly and burning themselves out. Without supernovae, galaxies would form stars at an uncontrollable rate, exhausting their gas and leaving behind lifeless collections of old stars. With supernovae, the universe maintains balance. Every supernova injects enormous energy into its surroundings. When thousands or millions of stars explode over time inside a galaxy, that energy adds up. Shockwaves from these explosions heat the interstellar gas, stir it, and keep it in motion. Hot gas does not collapse easily. By keeping gas turbulent and warm, supernovae slow down star formation. This delay is critical. It allows galaxies to form stars over billions of years instead of burning through their fuel in a short burst. The slow, steady rhythm of star formation we observe today exists because supernovae keep resetting the conditions. Supernovae also shape the structure of galaxies. Repeated explosions carve out vast cavities in the interstellar medium. These bubbles of hot gas expand, merge, and sometimes break through the disk of a galaxy, venting material into surrounding space. Over time, this process creates complex patterns of dense clouds and empty regions. Stars tend to form along the edges of these bubbles, where gas has been compressed by shock waves. In this way, supernovae do not just suppress star formation. They guide it, determining where and when new stars are born. On larger scales, supernova-driven winds can escape entire galaxies. In smaller galaxies with weaker gravity, these winds can remove a significant fraction of gas. This limits how massive those galaxies can become and explains why many small galaxies contain few stars. The material expelled does not vanish. It travels into intergalactic space, carrying heavy elements forged in stars. Over time, this enriched gas becomes part of the larger cosmic environment, influencing future generations of galaxies. This process connects individual stars to the evolution of the universe as a whole. A supernova occurring in one galaxy can affect regions far beyond its origin. The energy and material it releases contribute to the chemical and thermal state of the space between galaxies. In this way, supernovae help shape not just galaxies, but the large-scale structure of the universe. Supernovae also play a role in keeping galaxies dynamic rather than static. The interstellar medium is constantly being stirred by explosions, winds, and radiation. This prevents gas from settling into a uniform distribution. Instead, it remains clumpy, turbulent, and uneven. This unevenness is essential for star formation. Stars form in dense pockets of gas created by compression and turbulence. Without supernovae maintaining this chaotic environment, star formation would become inefficient or cease altogether. The Milky Way offers a clear example of this balance. Our galaxy experiences supernova explosions roughly once every few decades. Each one contributes to the ongoing circulation of gas and energy. The hot gas created by these explosions fills large regions of the galaxy, while cooler gas collects in dense clouds where new stars form. This cycle has continued for billions of years, allowing the Milky Way to remain active and structured. Supernovae also influence the distribution of elements within galaxies. Heavy elements produced in stars are released and mixed by explosions. Over time, this mixing spreads elements evenly, ensuring that future stars and planets have access to a rich chemical inventory. Without this mixing, elements would remain locked inside individual stars, and chemical complexity would be limited. Supernovae turn isolated stellar processes into shared galactic resources. In extreme cases, bursts of supernova activity can reshape entire galaxies. When many massive stars form at once, their combined explosions can create powerful galactic winds. These winds can halt star formation temporarily, alter galaxy shapes, and even affect neighboring galaxies. Such events are common in the early universe when star formation rates were much higher. Supernovae were more frequent, and their influence was correspondingly stronger. The modern universe is quieter, but it still carries the imprint of that earlier, more violent era. Supernovae also interact with other galactic forces. Their energy works alongside radiation from stars and activity from central black holes. Together, these processes regulate galaxy growth. No single force dominates forever. Gravity pulls inward, energy pushes outward. The balance between them determines the pace of cosmic evolution. Supernovae are one of the key contributors to that balance. Perhaps the most important role of supernovae is that they connect different generations of stars. A star forms from gas enriched by past explosions. It lives its life, producing energy and new elements. Then it may die in a supernova itself, returning even more material to space. This cycle repeats across billions of years. Galaxies are not collections of independent stars. They are ecosystems, sustained by continuous recycling, driven largely by supernovae. This perspective changes how we see stellar death. A supernova is not a failure or an endpoint. It is a necessary process that keeps galaxies alive. It prevents stagnation. It spreads resources. It creates diversity. Without supernovae, galaxies would be simpler, poorer, and far less dynamic. When we observe distant galaxies, their brightness, color, and structure all reflect the history of supernova activity within them. The universe we see today is the result of countless explosions shaping matter over immense timescales. Supernovae are the hidden architects behind that structure. A galaxy is not built quietly. It is built through repeated moments of violence carefully balanced over time. Supernovae are the rhythm that keeps that balance alive. Every discussion about supernovae eventually leads to a quiet but unavoidable realization. Without them, nothing complex would exist. Not planets, not oceans, not chemistry, not life. Supernovae are not just distant cosmic events. They are the reason matter was allowed to become interesting. They are the reason the universe moved beyond simplicity. In the beginning, the universe contained almost nothing but hydrogen and helium. These light elements were enough to form stars, but not enough to build complexity. Inside stars, fusion created heavier elements, but most of those elements remained trapped deep within stellar cores. Without a mechanism to release them, the universe would remain chemically poor. Supernovae provide that mechanism. They tear stars apart and scatter their contents into space, distributing elements that would otherwise never leave their place of origin. Carbon, oxygen, nitrogen, silicon, iron. These elements are not rare by accident. They are common because supernovae spread them efficiently across galaxies. Every explosion enriches the surrounding gas, increasing the chemical diversity of the universe. Over time, repeated supernova transform simple hydrogen clouds into complex mixtures capable of forming rocky planets and organic molecules. This transformation is gradual, cumulative, and irreversible. The Earth itself is built from supernova material. The iron in its core, the silicon in its crust, the oxygen in its atmosphere all originate from ancient stellar explosions. Long before the Sun formed, supernova enriched the cloud of gas that would eventually collapse into our solar system. The Sun inherited that material. The planets inherited it from the Sun. Life inherited it from the planets. This chain connects every living thing directly to stars that died billions of years ago. This connection is not poetic exaggeration. It is literal. The calcium in your bones, the iron in your blood, the carbon in your cells were forged in stars and released by supernovae. Life did not arise despite stellar death. It arose because of it. Supernovae are not enemies of life. They are prerequisites. Supernovae also shape environments in ways that influence habitability. The explosions that enrich space with heavy elements also trigger new rounds of star formation. Shockwaves compress gas clouds, causing them to collapse and form new stars. Many of those stars form in clusters that include long-lived, stable stars like the Sun. Without earlier supernovae triggering and enriching these regions, stars capable of hosting habitable planets might be rare or non-existent. At the same time, supernovae introduce danger. An explosion occurring too close to a developing planetary system can strip atmospheres, sterilize surfaces, or disrupt orbits. This creates a delicate balance. Supernovae must be close enough to enrich and stimulate star formation, but far enough away to avoid destruction. The fact that life exists at all suggests that this balance has been achieved many times across the universe. This balance also explains why life may be rare or fragile. Too few supernovae, and the universe remains chemically simple. Too many, and environments become hostile. The universe does not optimize for life intentionally. It simply follows physical laws. Life appears only where those laws produce the right combination of stability and change. Supernovae are central to that combination. On a deeper level, supernovae reveal how life is connected to cosmic time. Life requires heavy elements, and heavy elements require multiple generations of stars. That means life cannot appear early in the universe's history. It requires patience. It requires cycles of birth and death spanning billions of years. Supernovae are markers of that long preparation. They show us that the universe had to mature before complexity could emerge. Supernovae also influence the long-term evolution of planetary systems. The distribution of elements determines the types of planets that form. Systems rich in heavy elements are more likely to produce rocky worlds. Systems poor in those elements produce gas giants or fail to form planets at all. The history of nearby supernovae shapes the architecture of entire solar systems before planets ever exist. Even after planets form, supernovae continue to play a role. Cosmic rays produced in supernova remnants interact with planetary atmospheres. They may influence climate, cloud formation, and chemical reactions. Some theories suggest that supernova-driven radiation may have played a role in early biological evolution by driving mutations or altering atmospheric chemistry. While these ideas remain under investigation, they highlight how deeply intertwined life and stellar death may be. This connection reframes how we think about supernova emotionally. They are not distant disasters. They are ancestral events. They are part of the deep history that made life possible. Every explosion is both an ending and a contribution to a much larger process that spans galaxies and eons. Supernovae also remind us that life exists in a universe that is not gentle. The same processes that create the conditions for life also carry the potential for destruction. There is no separation between creative and destructive forces. They are two expressions of the same physical laws. Life emerges not in spite of this reality, but because of it. When we look at the night sky, we see stars as steady points of light. But behind that calm appearance lies a cycle of violence and renewal. Stars form, stars burn, stars die, and their remains seed future generations. Life is embedded within that cycle. We are not separate from it. We are products of it. A supernova is the universe breaking a star apart so that something else can exist. It is destruction with a purpose written into the laws of physics. And every living thing carries that history quietly within itself. Not all supernovae end at the same level of violence. Some push far beyond what was once thought possible, releasing energies so immense that they briefly rival the total output of entire galaxies. These extreme stellar deaths reveal that even among supernovae, there are limits waiting to be tested and, occasionally, broken. They show us how far nature can go when mass, gravity, and energy align under the most intense conditions. In the most massive stars ever formed, the collapse process can unfold in a way that is fundamentally different from ordinary supernova. These stars are born enormous, containing tens or even hundreds of times the mass of the Sun. Their cores grow heavy rapidly, and their internal conditions become extreme early in their lives. When they finally lose stability, the result is not a partial explosion followed by collapse, but total annihilation. The star tears itself apart so completely that no remnant remains. There is no neutron star. There is no black hole. The star is erased. In these rare cases, the physics inside the core becomes dominated by high-energy radiation. Photons convert into particles, removing the pressure that once supported the star against gravity. Collapse accelerates. Fusion ignites explosively throughout the core, and the entire star detonates at once. The explosion is so powerful that it leaves nothing behind. These events release unimaginable amounts of energy and scatter enormous quantities of heavy elements into space in a single moment. Such explosions were likely more common in the early universe, when stars could grow much larger than those we see today. The first generations of stars formed from pristine gas, free of heavy elements. Without those elements to regulate fusion and radiation, stars could grow to enormous sizes. When they died, they did so violently, shaping the chemical and structural evolution of the young universe. These ancient explosions may have played a crucial role in enriching the universe and setting the stage for later generations of stars and galaxies. Even among more typical supernovae, there are extremes. Some explosions release far more energy than average, shining brighter and lasting longer. These events challenge models of how explosions are powered and sustained. They suggest that under certain conditions, energy from newly formed neutron stars or black holes can continue driving the explosion long after the initial collapse. Magnetic fields, rotation, and relativistic effects combine to amplify the violence. In some cases, the newborn remnant becomes a rapidly spinning neutron star with an exceptionally strong magnetic field. As it slows down, it releases energy into the expanding debris, re-energizing the explosion. This additional input can make the supernova far brighter than usual and keep it glowing for extended periods. These events blur the line between stellar explosions and the energy output associated with compact remnants. There are also stellar deaths that appear, even more energetic than supernovae, associated with intense bursts of gamma rays. These events are among the most powerful explosions observed since the Big Bang. They release focused beams of energy that travel across the universe, briefly outshining everything else in gamma-ray light. While their exact mechanisms are still being studied, they appear to be connected to the collapse of rapidly rotating massive stars into black holes. These events show that stellar death can produce not just explosions, but highly directional jets that concentrate energy to an extreme degree. What makes these extreme deaths so important is not just their power, but what they reveal about physical limits. They test our understanding of how much energy can be released in a single event, how matter behaves under extreme radiation pressure, and how gravity interacts with rotation and magnetism. Each extreme supernova forces scientists to reconsider assumptions about stability, collapse, and explosion. These events also have far-reaching consequences for their environments. The immense energy they release can strip gas from entire regions of space, suppressing star formation for millions of years. At the same time, the heavy elements they eject enrich the universe on large scales. A single extreme explosion can influence the evolution of an entire galaxy, especially in the early universe when structures were smaller and more fragile. Despite their rarity, extreme supernovae leave lasting fingerprints. Their chemical signatures can be detected in ancient stars, revealing details about explosions that occurred billions of years ago. Their remnants may shape large regions of interstellar space. Their energy may contribute to the background radiation that fills the universe. Even long after they fade from view, their influence persists. These most violent stellar deaths remind us that the universe does not operate at a single scale of intensity. It allows variation. It allows extremes. Under the right conditions, processes can escalate far beyond what is typical. This openness to extremes is part of what makes the universe capable of producing such diversity and complexity. At the same time, these events are rare for a reason. They require precise conditions that do not occur often. This rarity helps maintain balance. If such explosions were common, galaxies might struggle to form stable structures. The universe would be too violent for long-term complexity. The fact that extreme supernovae are exceptional rather than routine is another sign of the delicate balance underlying cosmic evolution. Extreme supernovae show us the outer boundary of what stellar death can be. They mark the point where stars stop leaving remnants and instead vanish entirely. They demonstrate that there is more than one way for a star to end, and that the universe explores all of those possibilities. A supernova is already a powerful event. These are supernovae pushed to their absolute limit. They show us how far the universe is willing to go. Supernovae do more than shape matter and energy. They also shape our understanding of time itself. Because they are so bright and so distinctive, supernovae act as markers scattered across the history of the universe. Each explosion is a timestamp, recording when and where a star ended its life. By studying these events across vast distances, astronomers can reconstruct the story of cosmic expansion and evolution with remarkable precision. When a supernova explodes in a distant galaxy, its light begins a long journey through expanding space. As that space stretches, the light stretches with it. Its color shifts toward the red, carrying information about how much the universe has expanded since the explosion occurred. By measuring this shift, scientists can determine how far away the supernova is and how long ago it happened. In this way, a single explosion becomes a measurement of cosmic time. Some supernovae are especially valuable for this purpose because they follow highly consistent patterns. Their brightness rises and falls in predictable ways. Their peak luminosity is closely linked to how they explode. Because of this consistency, astronomers can compare how bright these explosions appear from Earth to how bright they must truly be. The difference reveals distance. These supernovae allow scientists to measure distances across billions of light years, far beyond what ordinary stars or galaxies can provide. Using these cosmic markers, astronomers discovered something unexpected. The expansion of the universe is not slowing down. It is accelerating. This realization reshaped modern cosmology. It revealed the presence of a mysterious influence now called dark energy, a force that counteracts gravity on the largest scales. Supernovae were central to this discovery. Without their predictable behavior and immense brightness, this acceleration might still be hidden from view. Supernovae also allow scientists to map how the universe has changed over time. By observing explosions at different distances, astronomers effectively look back through history. Nearby supernovae show us the universe as it is now. Distant ones show us the universe as it was billions of years ago. Comparing these events reveals how star formation rates, galaxy environments, and chemical compositions have evolved. Supernovae become a timeline written in light. These observations show that the universe was once far more active. In its youth, stars formed rapidly, lived briefly, and died violently. Supernovae were more frequent. Galaxies were smaller and closer together. As time passed, expansion slowed interactions, star formation declined, and supernovae became less common. The modern universe is calmer, but it carries the imprint of that earlier intensity. Supernovae are the evidence of that transition. Supernovae also help scientists test whether the laws of physics have changed over time. By comparing distant explosions to nearby ones, researchers can check whether fundamental processes behave the same way across billions of years. So far, the universe appears consistent. The same physics governs stellar death now as it did when the universe was young. This consistency is one of the most reassuring discoveries in science. It suggests that reality operates under stable rules, even as conditions change dramatically. Observing supernovae across cosmic time is not easy. Their light is faint by the time it reaches Earth. Dust can obscure them. Their signals must be separated from the glow of entire galaxies. Yet with modern telescopes and careful analysis, astronomers continue to find these explosions at ever greater distances. Each new detection extends our view deeper into the past, revealing how the universe behaved closer to its beginning. Supernovae also serve as checkpoints in the story of cosmic structure. They show where stars formed, how galaxies evolved, and how matter moved through space. The distribution of supernovae traces the distribution of stars themselves. By mapping where explosions occur, scientists can infer where star formation is most active and how it changes over time. Supernovae become guides to understanding galactic ecosystems across the universe. There is also something deeply symbolic in this role. A star's death becomes a tool for measuring the life of the universe. The moment when a star fails becomes the moment when knowledge advances. Supernovae turn endings into information. They transform destruction into insight. Even today, new surveys search the sky continuously, waiting for the sudden appearance of a supernova. When one is detected, telescopes around the world turn toward it. Scientists capture its light across every wavelength, from radio waves to gamma rays. Each observation adds detail to our understanding of how stars die and how the universe expands. Through supernovae, the universe reveals its age, its size, and its history. These explosions allow us to place ourselves in time, to know not just where we are, but when we are. They show us that we live in a universe that has been evolving for billions of years and will continue to change long after our era has passed. Supernovae remind us that time in the universe is not abstract. It is recorded in events, in light, and in structure. Every explosion is a marker on that timeline, a bright point that tells us something about the past and hints at the future. A supernova is a star's final act, but it is also a clock, a ruler, and a message sent across time. Through these explosions, the universe tells us its story. When everything about supernova is taken together, one truth becomes clear. These explosions are not rare accidents or violent interruptions. They are part of the universe's design. They are how the universe renews itself, redistributes its matter, and moves from simplicity toward complexity. Supernovae are not exceptions to cosmic order. They are expressions of it. A star spends its life holding itself together against gravity, producing light, warmth, and stability. That long struggle creates structure. But structure alone is not enough. Without release, without transformation, the universe would stagnate. Supernovae provide that release. They break open what has become too stable and spread its contents outward, allowing new systems to form. In this way, supernovae are not failures of stars. They are the completion of a process. Across cosmic time, this process repeats endlessly. Stars form from enriched gas, they shine, they die, Their deaths seed the next generation. Galaxies grow not by preserving every star, but by allowing stars to end and contribute their material back to space. Supernovae are the turning points that make this cycle possible. Without them, the universe would be quiet, uniform, and lifeless. Supernovae also reveal something profound about how change happens in nature. The most important transformations often occur suddenly, after long periods of stability. A star may appear calm for millions of years, but its fate is decided in seconds. Those seconds shape everything that comes after. This pattern appears everywhere in the universe. Long balance followed by brief upheaval. Stability followed by release. Supernovae are the clearest example of this rhythm written on the largest possible scale. They also remind us that destruction and creation are not opposites. They are partners. The same explosion that tears a star apart creates the elements needed for planets, oceans, and life. The same shockwave that destroys structure triggers new formation elsewhere. The universe does not separate these processes. It combines them into a single continuous flow. Even our understanding of the universe depends on supernova. Through them, we measure distance. Through them, we measure time. Through them, we discovered that the universe is expanding faster and faster. Stellar death has become one of the most powerful tools for understanding cosmic life. This connection between destruction and knowledge is not accidental. It reflects the deeper logic of the universe, where information is carried by change. Supernovae also place our existence into perspective. Life did not emerge in a gentle universe. It emerged in one shaped by repeated violence, balance, and renewal. The conditions that allow us to exist were forged through countless explosions long before the Earth formed. Every stable environment rests on a history of instability. Every quiet moment in the cosmos is built on ancient chaos. When we look at a supernova in the sky, we are seeing more than an explosion. We are seeing a boundary between eras. We are seeing matter change its role. We are seeing gravity complete its work and hand the result back to the universe. That light carries the memory of a star's entire existence and the promise of what its remains will become. Supernovae also tell us something honest about the future. Stars will continue to die. Galaxies will continue to evolve. The universe will continue to change through cycles of buildup and release. Nothing lasts forever in its current form, but nothing is truly lost. Matter changes shape. Energy changes direction. Structure changes scale. The universe moves forward by letting things end. In the end, supernovae are not just events we observe. They are processes we are part of. The atoms in our bodies, the planet beneath our feet, and the star that warms our world all trace their origins back to these explosions. We live inside a universe shaped by supernovae, even if we rarely think about them. A supernova is a star's final light, but it is also the universe opening a path forward. It is the moment balance breaks so that something new can exist. And through these endings, the universe continues to grow. Supernovae remind us that the universe grows by letting stars end. Every explosion reshapes space, spreads new elements, and prepares the next chapter of cosmic evolution. What looks like destruction from a distance is, in reality, the universe moving forward.